Good afternoon, everyone. Today, I'll talk about universal law at the edge. I'll try to justify this title as we go along. This work is done with Professor Manas Anupam Satya, David, and Gregory, and this is based on two of these articles. So, a class of third order phase transitions called push to pull phase transitions have been observed in many systems. So what do I mean by push to pull phase transition? So if you look at this figure here, it's a figure of a density profile of a log gas. Log gas is the Coulomb gas in 2 dimension when it is confined to 1 dimension. And you see this is the equilibrium density profile. The particle at the edge, if you take a note at the particle at the edge, if you want to bring this particle out of this bulk region, it will cost you some free energy. Similarly, if you want to push this particle into the bulk, it will cost you a different amount of energy. So this difference in energy actually leads to a phase transition. And that's what we would like to study for a different model. What has been done is actually this has been done for log gas in the context of random matrix theory in many models, and which maps to log gas. And this phase transition is connected to the edge statistics. So there are other studies where people have studied Coulomb gas in higher dimension in arbitrary potentials. There they see that again the phase transition is of the third order kind, and then they have studied screen Coulomb gas also in arbitrary potentials. Again, there is a third. This push to pull phase transition is third order. So this actually raises a question: how general is this phase transition? So in this study, what we have done is we have studied the distribution of the edge particle, especially, more precisely, the edge distribution of the edge particle. Edge in the sense, what I mean is the tails of the distribution for a harmonically confined system where the interactions between the particle is of the power law form. Why did we choose a power law interaction? So this power law interaction, basically this interaction, the special limits of this interaction, for example, k equals to -1 maps to the previous studies. Similarly, k tending to 0 for a special limit of j again tends to the previous model. So this sort of is a general model, and there are some more features here. For k greater than 1, this is a short range model. For k less than 1, it is a long range model. And other values of k are, quite interesting also. For example, k tending to infinity is a hard rods. K tending to 2 is a Calogero model, which is an integrable model. So this sort of captures quite a few interesting physics, models with different physics. So what we have done in this, what I will show in this talk is how the atypical fluctuations behave. In particular, how the left and right large deviation function behave. And these left and right large deviation functions are effectively the free energy cost in pushing or pulling the edge particle out of this density profile. And hence we can study the order of transition. So to start with, we would like to find the distribution of Xmax. So we start with a CDF, a cumulative distribution function. So Xmax is the maximum of all the particles. So in this, what this means is the maximum position of the particle is smaller than W. That means all the particles have to be smaller than the wall position. And this actually eventually just becomes the ratio of the partition function of the gas in the presence of wall and in the absence of wall. So everything will boil down to solving this partition function. So this is the partition function in the presence of wall. Now, if you look at the energy function, it's actually seems quite difficult to do this. Only special limits can be computed exactly in these variables as it is. For example, k equals to -1 and k tending to infinity. I'm not aware of other models where it can be computed exactly in this particular way. Maybe k tending to 0 also. But what we can do is, instead of doing this microscopic calculation, we can do a variable transformation. We don't study the microscopic this integrals. We go to macroscopic variables and do this field theoretic formulation. And using that field theoretic formulation, we just have to solve this partition function. Now the difficult question is, how does the energy microscopic energy looks in a macroscopic variable. And that has been luckily done by one of the previous works of the group, where they found this energy function for short range model, which is k greater than 1, and long range model k less than 1, which is known before also. So we have this partition function, and in this partition function, there's the energy, which is basically this term, and there's this entropy term, which is a Jacobian of the transformation, because we have done a variable transformation. So there will be a Jacobian involved in the transformation. And this is basically configurational entropy. And this is a delta function, which ensures that whatever density I get has to be normalized. So that's what we like to compute this partition function. What previous studies, this Sana et al., what they have noticed is that the energy function itself has a system size scaling behavior, where it's super extensive with this action given by E tilde, which is a scaled energy, and this scaled entropy, and this is just a Lagrange multiplier. We would like to solve this partition function. Now you notice that there is an n to the power 2 alpha k plus 1 sitting here. So in the large n limit, minimizing this action will give us the partition function. So that's what we would like to do. But notice, before we do that, we notice that the energy is of the order 1, but the entropy is order n to the power minus 2 alpha k, so which is extremely small. So that means we can effectively ignore the entropy term, only energy matters, and the Lagrange multiplier, of course. So using this, we minimize this action, which gives us a saddle point equation. From saddle point equation, what we notice is, we have to compute the partition function in the presence of wall and in the absence of wall. So in the absence of wall or presence of wall, what we notice is the support has to be finite, in the sense that the density profile cannot have infinitely extended density profiles. The system cannot have infinitely extended density profiles. So this work has been done in the absence of wall by Sana et al. Here what we have done is, in the presence of wall, what we notice is, as the wall is pushed, not the wall, as the wall is brought closer, below this particular unconstrained profile, as you can see, it's a finite support. So if the wall is present in this region, the system will not notice that there exists a wall. So as you bring the wall from infinity closer and closer, at exactly this point, it will start feeling the wall, and the density profile will start changing. And as we push, more and more particles will get accumulated at the wall. This is for short range model, k greater than 1. Now, in k less than 1, what happens is the behavior of the, So once we know this density profile, we can substitute back here and compute the partition function. That's what we are going to do. But next we study the other regime where the interactions are long ranged. Here, what we have seen is the interaction, since they are long range, they have a different free energy function itself is different. That gives a different saddle point equation, and one has to solve it in the presence and absence of wall. Again, it has been found that it actually has a finite support. So as you start pushing the wall, it won't feel the presence of wall for a really long time, and suddenly it starts feeling the presence of wall, and the particles will start accumulating at the wall. But here, compared to previous regime, here there was a finite density at the wall. Here there is a diverging density. It's an integrable divergence, but nonetheless diverging. So basically, for a long range model, more and more particles are coming closer and closer near the wall. So and this, as we reduce k, make it more and more long ranged, what happens is the divergence, this is w minus y to the power k minus 1 by 2, it becomes more and more more divergent, which makes it at k equals to -1 non-integrable. So this solution will start failing for k equals to -1 and less than -1.
So Jitendra, you have 3 minutes left.
Okay. What? K less than -1. In this regime, -2 to -1, it's again, we have to solve this, but the previous solution was not working. So what we did was check the Monte Carlo simulation, and we saw that the integrable diversion has become a delta function, and this delta function has pushed the remaining particles, creating a whole region and a bulk region. And using this as an ansatz, we can solve this integral equation to get how the bulk density profile looks and what will be the strength of the delta function. But in the absence of wall, it has already been done. In the absence of wall, it was actually, instead of dome shaped, it was U-shaped. Here, the U-shaped behavior is there, but there is an additional hole and this delta function, which is different. So now we have densities in the presence and absence of wall for all three regimes. Now we have to compute the probability of Ymax less than W, which is the ratio of the partition function, which basically becomes e to the power minus beta n to the power 2 alpha k plus 1 phi minus. This is the energy cost in pushing the particles to the bulk. And that's what we have to compute here. We have the expressions of E tilde, so we can compute this. And now notice that when the wall is away from LKUC, I mean to the right of LKUC, this becomes 1, which basically means that the CDF is 1. That means most of the particles will not go away from LKUC. So this is not a good way to compute how the right fluctuations look like. So to compute that, we actually, instead of looking at CDF, we look at PDF. And PDF turns out to be the energy cost in exponential of energy cost in removing the particle from the edge to the right. That's what this is. So this difference in energy costs tells us that the probability distribution is changing behavior. So for example, when the wall is greater than smaller than LKUC, then we have an energy, probability distribution is like this. When the wall is less than greater than LKUC, the probability distribution is like this. So this suggests that there is some sort of transition here. This is basically energy per particle like thing, some sort of transition, and this transition is determined by the behavior of phi minus. And the next task is to study how the phi minus behaves as the wall approaches the unconstrained density profile. So in this slide, I see that we compute the large deviation function using Monte Carlo simulation and compare it with the theory, and the match is decent. So next important task is to compute how phi minus behaves when wall is close to LKUC, and we see that it's actually proportional to EK minus LKUC minus W to the power EK minus, and this suggests that the third derivative of phi minus, which is like 2 plus 1 by k, and then is discontinuous, which suggests it's a third order phase transition. In the regime -2 to -1, -1 to 1, the free energy was different, so the field theory is different, and we compute phi minus in this regime, and we see that asymptotic behavior, we see that the third derivative again is discontinuous. Similarly, in this regime, the density profile itself was different. So this actually was again suggests that phi minus, the asymptotic behavior of phi minus is similar, and it's again a third order phase transition. Since it's a third order phase, that's what we wanted to do. It turns out it's third order phase transition for our general K, even if the model is short ranged or long ranged. In conclusion, what we have done in this study is computed how the density behaves in the presence of wall. So when K is extremely large, the density gets accumulated at the wall. The particles get accumulated at the wall. As we reduce the value of K, more and more particles gets accumulated at the wall, and that accumulation becomes so strong that eventually at K equals to -1, it becomes a delta function. And for K less than -1, it starts pushing the remaining particles. This is like a supercharge which starts pushing this region and creating a larger and larger hole. And using these density profile, we computed the large deviation functions, which basically characterize the atypical fluctuations. And once we have the expressions of large deviation function, we can do the asymptotics. And from asymptotics, we find that the order of transition is third order. Thank you.
So how robust is this third order phase transition with respect to the confining potential?
Yeah, so what has been...
first question is that, and second question is, you had one particle interacting with every other particle.
Yeah.
If you relax this, then does the order of phase transition change?
Yeah, so that's true. It will definitely change, but if it's still okay, I'll first answer the first question. That is, what happens when the external trap is different? So for Coulomb gases, they have studied this for different external trap, and they see that it is third order phase transition. But for in our model, we haven't done that study, but I mean, at least I strongly believe that it will still be a third order phase transition for k less than 1. I'm not sure about k greater than 1. As for the second question, which was, what was the question? Sorry.
If instead of every particle interacting with every other particle, there's finite interaction.
Yeah, for when D basically is the how many particles it's interacting. If D is order 1, then I don't think this will happen. When D is order system size, then the field theory itself is quite similar. And it's not well known, but it probably is quite similar. So I would expect that it will have similar behavior, but I do not have an answer there.
One more follow-up. If temperature becomes important, then do you expect any
temperature
change?
becomes important, the density itself will spill over. So when we start pushing the wall, I mean the effect of wall will be felt always. So the edge particle is literally at infinity, because it's, so I'm not sure about what will happen to the phase transition.
Okay, so I mean, so normally like in phase transition, let's say some physical quantity, I mean, there's this transition, right?
Yeah.
So here, I mean, like, is there a simple physical observable? So I mean, which is some third derivative or something of the free energy, which shows some like.
So here the free energy itself has the third derivative, which is discontinuous.
Really, what is it? I mean,
basically you're asking what is the order parameter of sorts, right?
Some physical observable which shows a transition.
So the density itself is a very good example, because initially the density, the edge, what is the density at the edge? That was 0. And suddenly as we start pushing the wall, the density becomes finite, infinite, and then delta function. So this itself probably is but we do not have an answer, but I think I would believe that this is a good indicator of a order parameter, yeah.
But
for example, pressure itself is a first derivative, but that
discontinue, like suddenly it goes from 0 to something, right? Not suddenly, slowly.
It slowly goes from, but there is no jump.
There's no jump, right? Yes.
Then we have to look at k, kappa. Then again we have to take a derivative of kappa.
But that's not something very physical.
Physical, yeah. So yeah.
Hello. Yeah. So do you know what happens in this kind of general K models if you turn on dynamics?
Dynamics, that's what we're working on, but I'm not sure about the transitions, what will happen to these transitions. I would expect the same thing for low temperatures. When high temperature is present, then there will be different things, but for low temperature I would expect similar behavior.
So let's look at just 0 temperature. If I just take one of these particles,
yeah,
and take it out of the edge,
yeah,
okay, and just displace it and leave it,
yeah,
then what happens, you know? And just time evolve it with the.
Oh, so this has to be done. We haven't done this yet, but what our preliminary study shows, I'm not talking about the transition or anything, just the dynamics, what will happen to the dynamics. It would do the oscillation, but one particle, I'm not so sure. It will probably not do a lot of things, because edge particles have very little energy cost to make. I mean, these are very small perturbations. If we do a bulk particle, this will be slightly larger perturbation. So it will probably just oscillate a bit and then go to a final, it will thermalize eventually. For some values of K, it won't thermalize. For other values of K, it will thermalize.
In the dynamics, do you think that this kind of third order phase transitions and atypical fluctuations, there's a way it will show up? Like, for example, if I try to write down some effective Langevin kind of thing for one particle,
okay,
which is just taken out, would I see these fluctuations? How, I mean, is that a one way of seeing these fluctuation of the edge and so on?
I couldn't follow the question. Can you repeat it?
So the same question where I just take one of the particles and I just take it out of the edge, right?
Yeah.
And then I try to look at the dynamics of that.
Okay.
So I'm asking these kind of fluctuations and so on you're talking about, atypical fluctuations. do you think that will show up in that dynamics?
Oh, okay. So the left large deviation functions will be quite rare, but the right large deviation function will be, I mean, it's possible to show up, but it won't be like these tails are these probabilities of the order 10 power minus 100. So they won't be easily, I mean, they can't be easily, most probably they won't be, but if we can shift the dynamics in such a way that these such low probabilities can show up. I mean, we have to add a forcing term on the edge particle to make sure that it's actually exploring the regions of low probability. So in principle, if you just do this, it won't show up on that level, but effectively we can design the system to get it. Basically, we have to, it's like an important sampling technique. We just push the particle by additional force and do a variable transformation to get back to the original.
Okay, so with this, we thank Jitendra for his talk. Yeah. So,